closely at these two beakers. One contains dilute hydrochloric acid, and the other holds dilute acetic acid. Visually, they are identical, completely clear and indistinguishable. Yet our goal is to prove which of these liquids is the stronger acid. To conduct a valid comparison, we've prepared both samples at exactly equal concentrations. Without this mathematical baseline, our testing would provide no meaningful data. We will use a two-part testing methodology. First, we'll establish a baseline with blue litmus paper, and then we will use a detailed universal indicator chart to measure the specific differences between the two. To perform these tests, we'll need the two indicators, clean glass test tubes, and pipettes for handling the acids. Identifying a substance as an acid provides its category, but chemical analysis requires measuring the exact magnitude of that acidity to understand its behavior. We begin by moving our samples into test tubes so we can observe the reactions side by side. First, we take a strip of blue litmus paper and dip it into the dilute acetic acid. We then take a second strip and dip it into the beaker of dilute hydrochloric acid. Both strips change color instantly. As the liquid is absorbed, the blue paper transforms into a bright, unmistakable red. Since both strips now look exactly the same, it would be easy to assume that these two acids are of equal strength. However, litmus paper only acts as a binary toggle. It can confirm the presence of an acid, but it cannot measure how acidic a substance actually is. Because both samples yielded the same red result, the litmus test is unable to show the difference between them. To find that distinction, we need a more sensitive tool. We now introduce a universal indicator solution, which provides the detailed measurements we need. We add an equal number of drops to both the hydrochloric and acetic acid samples. The formerly clear liquids immediately diverge into two different colors. By holding these samples against a white background, we ensure the colors we see are accurate and not distorted by the lighting in the room. The numerical pH scale translates these colors into data. Hydrochloric acid turns deep red, corresponding to a low pH of 1 to 2. Acetic acid is lighter orange, indicating a higher, less acidic pH of 3 to 4. Despite having the same starting concentrations, the discrepancy in their pH levels is the proof that hydrochloric acid is structurally stronger than acetic acid. To understand this difference, we have to look past the colors and examine the behavior of the molecules within the liquids. This difference is due to ionization, how molecules break apart in solution. Hydrochloric acid ionizes completely, fracturing every molecule to release a high concentration of hydrogen ions. Acetic acid, a carboxylic acid, behaves differently, only partially breaking apart. This partial ionization results in a much lower concentration of free hydrogen ions, which keeps the pH from dropping as low as the hydrochloric acid. Ultimately, an acid's strength is defined by this mechanical willingness to ionize, rather than the amount of acid poured into the beaker. By following this protocol, we have successfully moved past visual appearances to isolate the strong acid from the weak. We've seen the contrast between the uniform red of the litmus paper and the distinct, meaningful colors provided by the universal indicator. Our final results are clear. The hydrochloric acid reached a pH of 1 to 2, while the acetic acid measured a 3 to 4. These color gradients connect directly to the molecular process of complete versus partial ionization occurring within the samples. You now have a framework for using both molecular theory and visual testing to correctly identify the strength of any acid you encounter.